Hi, folks, and welcome to an introduction to heat exchangers. In the next few weeks, you're going to be having a lot of homework problems that are focused or that involve heat exchangers. And I wanted to give you a little introduction to what a basic heat exchanger is all about, what it does, what it looks like. So here we go. Introduction to heat exchangers. All of these images on the screen are examples of heat exchangers, different types. And so I'm going to try to cover these as we go through, but what they have something in common. So let's look and see what they have in common. And like I say, you're going to be reading in your homework problems, a heat exchanger does such and such. This is what should come to your mind. Okay. So the basic objective of any heat exchanger, well, it's a little bit obvious, is to exchange heat from one flowing fluid to another. And so this is a generic example of a shell and tube heat exchanger. And let's see how this relates to your thermo class. Well, I can see that we've got flow in and out. So clearly this is an open system. In our study in this class, we're going to say that that each flow is steady at all these positions. So obviously this heat exchanger can't get fatter or skinnier. It's made out of steel usually. And also then the states at all these different positions, they're steady in time. They don't depend on time. So our model is going to be steady state, steady flow, open system. Now, usually, since we're trying to transfer heat from one fluid to another flowing fluid, we've usually got two inlets and two outlets. In this sketch, let's see, here's an inlet here, and here is an inlet here. Here's an outlet, and here's an outlet, two inlets and two outlets. And another thing to remember that some students ask about is the streams do not mix. The mass flow from the hot fluid does not interact physically with the cold fluid. The streams do not mix. They are held separate. Okay, so now it's time to go live. I'd like to try to show you how you could build a heat exchanger with components you get at the hardware store, whether it's Home Depot or Lowe's. Okay, so I've gone to Lowe's and I've bought a piece of 2-inch PVC pipe. Okay, well, this is going to be the shell. So we're going to have fluid flowing through this PVC pipe. And so I've taken the time already offline. I've drilled a hole in this side of the pipe, okay, and I put a little 1-inch or 1/2-inch connection there, and I've drilled a hole here. So we're going to have flow sort of flowing within this pipe this way. Okay, and so let's see, I'll go ahead and put this on here now. So we're going to hook up our inlet to our PVC pipe. So there's the inlet. So notice I've got an arrow showing the direction of flow, and here's an outlet, and I'm showing the outlet. Got to back up here a little bit. Okay, so let's see. Okay, so I've got flow inside my 2-inch pipe. So let's say I've got cold liquid flowing in this PVC pipe, and now I bought a copper tube, and I've got hot liquid in here. So my objective is to transfer heat from this hot inside fluid flowing inside this copper tube, hot, to this cold fluid flowing in here. So let's see, what I did was I bought a couple of end caps and drilled holes in them. So, all right, so I'm going to put an end cap here, and I'm going to insert my copper. I got it, okay? And so what I'm doing is I'm fitting my copper pipe right in the middle of my PVC pipe, and I've got my last end cap that I've drilled a hole in. And I'm trying to fit it fit, okay. All right, so now I've got my copper pipe inside, so I've got the hot fluid flowing in. And so let me show, I've got a little marker to show some direction. So I've got a rod here that I'm going to put in my copper pipe to show that I've got flow flowing in there. And then I've got a marker so that I have fluid flowing out there. Okay, so let's see what have I built here. I've built a 2-pipe heat exchanger. And let's see, let's characterize the way the fluid is flowing. I've got fluid flowing in here. This is the cold, and hot fluid flowing in here. And do you see that the streams they're flowing parallel with each other? And so the hot fluid is cooling off and the cold fluid is warming up until finally I've got the outlet of my hot fluid here and the outlet of my cold fluid coming in here. And I bet this is going to be warmer than the inlet. And I'll bet this is going to be colder than the inlet. So I've just built a 2-pipe parallel flow heat exchanger from stuff I bought at Lowe's. Now you're thinking, well, if he hooked this up to hot water and cold water, we'd have leaks all over the place. We would, right? Because I've just sort of pushed the copper tubing through the end caps. I would have to take some goopy stuff and seal this up to make this operational. But the purpose here is to show you that it is not that tough to build a heat exchanger. Now, there's a lot of technology that goes into building an industrial heat exchanger, but you could do this at your own house or in a lab. All right, so I'm going to set this down and we'll go back to the slides. Okay, and so that brings up a sketch of, I tried to depict in a sketch what I just showed you here live, a basic 2-pipe parallel flow heat exchanger. And so what are we going to do with that? Well, we'll start with a sketch and we'll number our inlets and outlets. So I've numbered my hot inlet as 1, hot outlet as 2, cold inlet as 3, and cold outlet as 4. You can number these any way you want. You could start at 56 if you wanted to, but you can number them any way you want. Okay. Open system, steady state, steady flow, 2 inlets and 2 outlets. And now this is a little teaser to the heat transfer class that you're going to be taking next year. About 25% or 30% of that class has to do with analyzing heat exchangers. And in that class, we introduce what we call a temperature map. We map the temperature on the y-axis versus the position on the x-axis. And so what I want you to do is see how it sort of makes sense. The sketch, see the flow from 1 to 2, it's kind of in position as we go, sort of with x increasing. But you can see on the y-axis, we start out hot with the hot fluid, and it gets cooler. Well, why is that? Well, we're starting in with the cold fluid, and the cold fluid is getting hotter. And what you can see with your eyes, and this has to do with your thermo class too, is recognize at any X position within the heat exchanger, there's always a temperature difference between hot and cold. So that's really a key thing to recognize. Remember, like the second day of class, we said, how do you pick out heat transfer? Well, you pick out heat transfer as a result. It's a boundary phenomenon. It's happening at this boundary right here, this hot to cold boundary. Okay, and there's a temperature difference between the hot fluid and the cold fluid, and I'm calling that delta T. So delta T for this problem, starting out big, and it gets lower and lower and lower and lower until delta T is a smaller number here. So that's your intro to heat transfer, class, but also an intro to you solving your thermodynamics problems that are coming up that may already have come up. I need to go live again. And what I want to do is look at my little homebrew heat exchanger, and I'm going to switch and I'm going to show you how to create a counterflow heat exchanger. Okay, here we are back. Okay, here was our parallel flow heat exchanger. I had hot flow in, cold flow in. The flow streams were in parallel. Hot flow out, cold flow out. All I have to do to make a counterflow heat exchanger is to remove my markers and put my outlet, the hot outlet here, and the hot inlet here. And so I hope that you can see with your eyes, I've just invented a two-pipe counterflow heat exchanger. So now look at the arrows, take a little time to see what you've got. And do you see that the hot fluid is going counter to the cold fluid? And we're going to draw a sketch, and we're going to look at the temperature map. And so what I'm going to try to convince you is that for the heat transfer surface area in the pipe. Now, could you, in your mind, can you figure out how you would calculate the heat transfer surface area? I'll bet you could. It would simply be the surface, the external surface area of this copper pipe. It would be L times pi times D of the copper pipe. That would be the heat transfer surface area. So for a fixed amount of surface area, you get more bang for the buck by going counterflow. And I hope you'll be able to see that from the sketch. Okay, so now just some notes on the basic two-pipe counterflow heat exchanger. We've still got hot in 1 and 2, hot out 2, cold in 3, and cold out 4. We've just switched the direction, but the numbering system is the same. Okay, so here's our sketch. Looks similar to the parallel flow, but now it's very clear that you've got counterflow. Now let's look at our temperature map. The hot fluid comes in hot at 1, it cools down. The cold fluid comes in at a cold temperature and heats up. And another thing to observe, a similarity, open system, steady state, steady flow, 2 inlets and 2 outlets. And notice how at all points here, there is a temperature difference between the hot fluid and the cold fluid. And now one thing that it's really cool that you see with your eyes, notice here how that this T4, this cold temperature, can actually be heated up hotter than the outlet of the cold. So it blows your mind, but it can be done. And we do this in industry all the time. And the only way to heat up T4 above T2 is to have the counterflow arrangement. And you're going to cover that, the reasons why, in about 2 weeks in your thermo class. Very powerful result. Let's move along. Okay. Now, sort of the purpose for this video in the first place, other than showing you how you could build a heat exchanger from Lowe's and that type of thing. Thermodynamic analysis, what you're going to be asked to do in your homework problems. You're going to start with a sketch. There's 2 methods I want to show you. Method 1, start with a sketch, draw your control surface, identify the heat transfer rate and the output power associated with the control surface you drew, and then write down the first law. That's what we're going to do. So here's our sketch. We're going to use two-pipe counterflow as a generic example. Okay, so we need to draw our control surface. Okay, I've drawn a dashed line around the whole thing. I've drawn a dashed line around this entire piece of equipment. Okay. Another thing is that we're going to go get some insulation from the back here, and we're going to imagine putting insulation around this heat exchanger shell. We're going to insulate the shell so there's no heat loss from the shell to the surroundings. So be aware of that. So we're going to insulate that. Okay. And so I'm going to show that on my sketch. It says the heat exchanger shell is fully insulated, keyword adiabatic. So synonym for fully insulated is adiabatic. All right, so I've drawn my control surface. I observe I've got 2 inlets and 2 outlets at my control surface. I've insulated this control surface here, the outside of the exchanger. I've insulated outside of the exchanger so that Q dot N to our control surface is 0. And do you see a shaft rotating coming from what we built? No, there's no rotating shaft of an open system. This open system is not lifting a weight anywhere. A weight's not being lifted, no rotating shaft. So W dot out is 0. So notice, okay, so I'm fleshing out my sketch. Now I'm going to write the first law. Q dot N minus W dot out equals. Now, in your mind, I didn't stretch out all of the painful details. I thought in my mind, first law, open system, 2 inlets and 2 outlets. I'm going to have the Q dot N minus W dot out equals the sum of the M dot leaving, H leaving, minus the sum of the M dot in, H in. So I've written this down. Sum of the exitings, M dot 2, H2, enthalpy. M dot 4, H4, leaving, okay? Minus what's coming in, M dot 1, H1, plus M dot 3, H3. Simple as that. I can simply, man, left-hand side easy, 0. Left-hand side of the first law, steady state, steady flow, 0. What else can I observe? I can also observe from the continuity equation that M dot 2 exactly equals M dot 1. I didn't drag that out on the slide. You've got that in your head now, okay? I can observe that M dot 3 equals M dot 4, steady state, steady flow, okay? So I made that substitution, left-hand side 0. I can simplify M dot 1, H1 minus H2 exactly equals M dot 3, H3 minus H4, okay? This is a simple but powerful result. That's method 1. And so look, how many variables do I have in this expression? I got 1, 2, 3, 4, 5. I've got 6 variables. But if you've got 5 of them, it's child's play to get that 6th one. Okay, so that's what you're looking for. You're looking for 1 equation and 1 unknown. And man, this is a simple equation based on the first law. Very important. So that was method 1. Method 2, we're going to start with a sketch. This time what we're going to do is we're going to draw 2 different control surfaces. We're going to draw a control surface associated with the copper pipe, the hot fluid only. Then we're going to draw a control surface related to the cold fluid only, and we're going to write down 2 statements of the first law. That's what we're going to do. All right, so here's the original sketch. And I've got 2 block arrows to say, look, here's what I'm going to bust up this original sketch into an open system, 1 inlet, 1 outlet, steady control volume for the hot fluid only. See how I've tried to show it blue and blue. I've done the same thing over here on the right side of my page. I've drawn a control surface for the cold fluid only. There's my surface, okay? 1 inlet, 1 outlet, 3 to 4, okay? We'll make that same argument about a shaft. Do I see a shaft rotating? No. Lifting a weight? No. So for both of these control volumes, open systems, W dot is 0. Now, is heat transfer involved? Yes. Heat transfer is involved. Let's look at the cold first. There's heat transfer involved in this open system. Q dot N from 3 to 4. Q dot N. Heat is being added to this open system from the hot fluid. So there's my sketch. Now, the hot fluid. Got to do a little thinking. Is heat flowing into this? No. Heat is rejected. However, for your sanity in class and your problem-solving skill, still show Q dot N from 1 to 2, show that arrow going in, and make a note that it is a negative number. Heat is rejected. Q dot N is less than 0 for the hot fluid. And then you do some thinking. You say steady state, steady flow. These two heat transfers have got to match exactly. And so you can say Q dot N from 3 to 4 exactly equals minus Q dot N from 1 to 2. Because this is going to be a negative number here. So minus a negative number. Okay. Important thing to realize. So this is method 2 for analyzing a heat exchanger. We'll write the first law. So to finish this out, we'll write the first law. First law for the hot fluid, Q dot N from 1 to 2, it's going to be a negative number, equals M dot 2 times H2 minus H1. That makes sense, doesn't it? As the temperature cools down, H2 is going to be a lower number than H1. Think about water. The enthalpy of water is going to decrease as the temperature decreases. Okay, so this is going to work out fine. First law for the cold fluid, Q dot N, positive, minus W dot out, 0, equals M dot, one inlet, one outlet, times H4 minus H3. That's making sense because we're adding heat, positive, and so the outlet enthalpy is going to be a bigger number than the inlet enthalpy. Think of water. Think of just water coming in. So it makes the outlet enthalpy bigger. And then you can also visualize. So now you can visualize, if you think about method 1, you can see that shows that Q dot N from 3 to 4 exactly equals minus Q dot N from 1 to 2. So with this information, you get exactly the same result as method number 1. But the benefit of this method is you can solve for the heat transfer from the hot to the cold. That's an advantage of this method. Okay, so you ask, which method is best to use? Well, both methods work, okay? The method you select depends on the information you're given and the information you're trying to determine. So, for example, if a homework problem says, how much heat is transferred from the hot to cold, you got to use method 2. So that's kind of a giveaway. Now, if you know both the math flows and 3 of the temperatures, then method 1 is the easiest. But you have to know 5 of the 6 unknowns in that method 1 energy balance to get that 6th one. Okay, that is the thermodynamics part of this video. And if you're in a great hurry, you can go ahead and bust out of here and that's it. But I've got a number of slides to show you some physical images of what real world industrial shell and tube heat exchangers look like. So I've added this at no extra cost to you. Okay. Here's our homebrew. So there's sort of a basic sketch of our homebrew heat exchanger. Not really example of a industrial heat exchanger, but close. Okay. Oh, the jargon. We refer to the fluid flowing inside the big diameter as the shell side flow. That's the shell side. The shell side. What's flowing inside the big diameter? What's flowing inside the little diameter is called the tube side flow. That is jargon that we use in industry a lot. And so if you're watching this, put in the back of your mind, make it look like you've really gotten something out of your college education. Shell side flow, tube side flow. We say this all the time. Here's a cutaway view of a basic liquid to liquid shell and tube heat exchanger. And what I'm going to show you is that this is characterized as one tube pass and one shell pass. That's a characterization of this piece of equipment. Let's see. Let's look at the tube side first. It's the easiest. The tube side. We're coming, the tube side, the red. Okay. We're coming into this sort of manifold, and the flow is being distributed into a bunch of tubes, a bunch of little tubes, okay? And so it's coming out into another manifold in which all the flow recollects and flows out as one flow in the tube side outlet. So we've got one tube pass. The tubes pass right to left, one pass, okay? Shell side coming in here. Now, although the shell side flow, you can see we have baffles to make the shell side flow go up and down and mix and exchange heat very effectively with those tubes. You see that still the overall flow of the shell side is left to right. So we've got one shell pass, one tube pass. Now, a little more complexity. Same shell and tube heat exchanger. Okay, let's look at the tube side here. We're going to come into the tube side manifold. The flow is going to be distributed into a bunch of little tubes. The tube side flow goes from left to right, recollects in another manifold. It makes a 180-degree turn in the manifold, redistributed into these little tubes, flows right to left, back to another manifold, and then one big flow going out. That's the tube side outlet. So do you see that the tube side makes two passes in the exchanger? So that's called two tube passes. The shell side is identical. We're coming in and we're going left to right in one pass. We've got those baffles, flows going up and down, but basically one left to right pass in this shell and tube heat exchanger. Okay, we're getting there. Another type of shell and tube heat exchanger is what's called a U-tube heat exchanger. U-tube heat exchanger. You can see, it's tough to see the outlet here, but on the shell, we've got an inlet and one shell pass coming in here. The baffles again, and ultimately there is a flanged connection back here that you can't see where the shell side exits. Now, but there's two tube passes. The neat thing about this is we have, let's say we're coming in on the lower side. We're coming into a manifold, distributed into a bunch of little tubes. And instead of having a manifold on the right-hand side, these tubes are just bent. They're bent in a 180-degree fashion through tube benders and then out back into this other manifold. And then tube side flow comes out in one big flow. So also two tube side passes, makes one U-turn within the shell. Here's an image that I couldn't resist including. So here is an example of a, you can tell the U-tube shell and tube heat exchanger here because of this sort of rounded end on one side with the manifold on the other. And these, this tube bank, this U-tube bank has been removed from the shell. So you can see what the tube bank actually looks like in reality. And if you want to download, you can go to my Canvas site and download this static PowerPoint file if you're interested in going to these various links to look at this with your own eyes, okay? There's a link to a YouTube video that takes 15 minutes that explains the ins and outs of the shell and tube heat exchanger. And so there is the link if you wish to look at it. 15 minutes to watch. Okay, another type of heat exchanger is called cross flow, not shell and tube, cross flow heat exchangers. And when you look at this image, I hope that many of you can identify what this basic image is all about. I'm going to give you a second to, can you identify this image? For those of you who work on cars, you'll recognize that this is a piece of a snapshot of a radiator core, which with the copper tubes, you'll have the jacket water cooling inside these copper tubes, and the air, as your car is moving through the surroundings, air is passing across these finned tubes. That's a cross flow heat exchanger. And so here we go. And so there's a sort of a nice schematic of how it all fits together. And so this would be an example of an air to liquid heat exchanger. The liquid is your jacket water cooling water, okay, on one side, on the tube side. On the other side, flowing in cross flow, is cool air entering from the grill of your car. Cross flow heat exchanger. Here's another example of a cross flow heat exchanger, which is the evaporator of your whole house air conditioner. If you live in an apartment or a townhouse, or I don't know, your family residence may have central air. And if you have central air down in the basement or somewhere back in a closet, is going to be a forced air conditioning system. And in the summer, this evaporator section is what's taking in the cold refrigerant that you've been studying inside. So the cold refrigerant saturated mixture is going into the tubes, and the air from the return air from your return air duct is blowing across those cold refrigerant tubes, and it's getting cooled down. So warm air is coming back from your living room, and then cool air is being resupplied back to your living room. So air to refrigerant heat exchanger in cross flow. Another example of a cross flow heat exchanger has to do with power plants. And this way, an economizer is the way that we recover waste heat from exhaust gas. And so what we do with that is we preheat boiler feed water. And so inside these tubes is going to be boiler feed water, where we're going to recover waste energy from the hot exhaust gas going up the stack, called an economizer. But this is a exhaust gas to water heat exchanger in cross flow. I think my last example is a very classic steam to air cross flow exchanger. For those of you who may have had a co-op job or a job in a large industrial building in the wintertime, we take in cold outside air for fresh air, and we need to heat it so the people working within very large buildings are comfortable. And so we take saturated vapor steam, admit that to the tubes inside this exchanger through a manifold, and what comes out is saturated liquid condensate. Air is blowing across those heated tubes and heating the air before it goes into the large manufacturing space from the cold air makeup. So classic example of a steam to air cross flow heat exchanger. We're getting near the end, don't worry. In a few weeks, you're going to be working a lot with condensers. And this is a picture of a very large power plant condenser. And I want to give you a heads up on, and this is also a heat exchanger and relationship of how things are working relative to your first law of thermodynamics, continuity equation, and ultimately the second law here in a couple of weeks. All right, so I've tried to show a sketch and hook it up with the image. Let's look at the sketch first. The sketch. Here is a cylindrical vessel. So go over the image, see how that cylindrical vessel. Okay, sketch looks like a cylindrical vessel. The equipment, cylindrical vessel. Coming in at one is steam. Steam at low pressure, it might be saturated vapor, it might be superheated vapor, or it might be a saturated mixture where the quality is 0.95 or 0.98. So steam is coming in here, and the objective is to condense that steam back to water. And that's exactly what this heat exchanger does. It condenses that steam, and as the steam condenses, it turns to water droplet, saturated liquid, right? And it drops down into this device called the hot well. Still, it's part of the cylindrical vessel. It's just sort of kind of like a bump added to the bottom of it. And here it is. This is the hot well. See, it's kind of like a little semicircular cylinder that's underneath the big cylinder. Okay. So water through gravity drops down as it is condensed. Okay. And then out it goes to be pumped away to be used for boiler feed water purposes. So that's the hot side of this heat exchanger, condensing the steam. Now let's look at the cold side. which is the tube side. Typically, we've got river water or cooling tower water or lake water, river water. I think I just said that. But anyway, we've got a supply of water that's relatively cool, about at the surroundings temperature, and it's coming into a manifold going through tubes. It's going to make a U-turn through this manifold, okay? Back it goes. And so as it goes through this heat exchanger, it's picking up energy by way of heat transfer from the steam. It's condensing the steam. And so the river water outlet at state 4 goes back to the river, just a little warmer than it came in, okay? Or back to a cooling tower to be cooled down, okay? So water comes in at one temperature, leaves at a warmer temperature. This is it. So you're going to be working thermo problems for this. So there's two ways to approach it. Blindly write down a formula, apply the formula, hope you take your test, hope you pass your test, and then you're done with it. Or you can think about how this relates to the first law, and you can start with the first law, do an energy balance, look at your continuity equation for steady flow, m dot 3 equals m dot 4, steady flow, m dot 1 equals m dot 2, and figure it out on your own. That's the preferred method. That's what I hope you are interested in doing. Okay, so there you go. No condensing problem is complete without a PV diagram. So I've depicted process 1 to 2 on a PV diagram for you. So we've got a little menu of possibilities for state 1. State 1 can be a superheated vapor, could be a saturated vapor, could be a saturated mixture that's typically pretty high quality, 0.95, 0.97, 0.98, okay? And so you can see the direction of the process. We're condensing, and finally, we come out of the hot well exactly at saturated liquid. And so that's a good thing to put in the back of your mind. That was just a great shortcut for me, understanding thermodynamic modeling when you're practicing as an engineer. It's almost like this state 2, it's almost like a giveaway. If you know the pressure inside the condenser, and it's pretty easy to measure the pressure in the condenser with a pressure gauge, then you know what state 2 is going to be. You can look up H2 immediately. And what does that temperature map look like? And so process 1, do you see the process 1 to 2? Let's go back a slide. Process 1 to 2. Oh, constant temperature pretty much. Okay. Temperature map on the y-axis. Well, 1 to 2, we're showing it as constant temperature. How in the world are we transferring heat at constant temperature? Answer it. Well, here's delta T. You're observing delta T with your eyes. So that's one way we're doing it. As we condense the steam, we're decreasing the enthalpy from 1 to 2. So even though the temperature is staying constant, we're decreasing the enthalpy by way of increasing the saturated liquid proportion and decreasing the saturated vapor proportion. That's the way we can have heat transfer at constant temperature, by condensing or boiling. Okay, the steam condenses to saturated liquid at constant pressure in this condenser. Okay, we've reached your introduction to heat exchangers. Things to remember: basic objective, the basic objective is needing to transfer heat from a hot flowing fluid to a cold flowing fluid. Steady state, steady flow, open system. Okay. Temperature map. That's getting a little ahead, looking ahead towards your heat transfer course, but it's a great illustration of delta T between hot and cold fluids. Very important part of thermodynamics. We showed you how to apply the first law of thermodynamics to analyze heat exchanger situations. I hope you're a little better at it. I hope you're a little better now at knowing how to attack your homework problems that involve heat exchangers. And then I tried to give you a very quick summary of what basic heat exchangers look like in industry and automotive and that type of thing. So there you go. I hope you enjoyed this intro to heat exchangers. Okay, I'm going to stop recording and hope to see you next time.